at the next mode of block cipher. It is the cipher block chaining mode, or in short we call it as a CBC mode. Okay, we call it as a CBC mode. In short we call it CBC mode. We have the same procedure like that of the electronic code book. We have first of all divide the given plain text into blocks here. So each block will have a predefined size of number of bits. Either it may be 64 bits, 32 bits, 128 bits. It is depend upon the given algorithm. So for that given algorithm, a particular size of the these blocks will predefine. The size of P1, P2, P3 are all equal there. Okay. So we have up to not P3 here. We have up to Pn. Okay. We have up to Pn. Here is dot here. We have up to Pn here. So it is divided into n blocks. So we have already know that if the last block, if we cannot form a proper block size, then we go for bit padding. We add some dummy bits to make it a full size block here. So we have already done with the distribution of the blocks here. Next we perform the XOR operations here. Okay. This is for encryptions operations. For encryptions we have to generate from the plain text, we have to generate the ciphertext here. Similarly, for all the plain text, we have to generate this ciphertext here. So first of all, we take an initialization vector. Okay, we take an initialization vector. The size of this initialization vector is equal to the size of the given blocks here. If this is of 64 bits, then this will be of 64 bits here. This will be again of 64 bits here. So we perform the XOR operations with the initialization vector. It is a predefined vector here. It's a number of bits, a well-known pattern of bits here of 64 bits. This must be same size of the plain text. Why? Because we have to perform the XOR operations here. We have to perform the XOR operations. If the size of these blocks and initialized vectors are different, then we cannot perform the XOR operations here. Okay, this is the XOR operations here. Okay, then by performing some encryption algorithm, we use a particular key here. Okay, we use a particular key here. Also the size of the key is same with that of the plain text here. Then we perform the encryptions here. Okay, encryption, we have a certain mechanisms of encryption of transformations here, either addition, multiplication, or it may be any other algorithms here that is running inside this encryption algorithm. Then we generate the ciphertext, and the size of the ciphertext, as you know, this one will be of 64 bits here. The size will be of 64. This is just an example. If the plain text blocks, if you have taken as 64 bits, then the size of the ciphertext for that particular instant will be of 64 bits here. So what happened? Next, we have to perform the same operations here. We have the plain text, we have to do the XOR operations. But here, instead of taking again the initialization vector here, I have a propagations here. Okay, I have a chain here of propagations from the previous block here, from this previous step, that is from this given output ciphertext. I take it as a chaining. Okay, as a chaining, and take this one as the input here. What is the size of this chaining? This is of 64 bits, so the plain text will be obviously of 64 bits. We have already known. Then if we'll perform the XOR operations here, we'll perform the XOR operations again, and then we'll do the encryptions here. Okay, encryption, this is the key size, this is the key. We perform the encryptions, and then we get the ciphertext here. Encryptions, and then we get the ciphertext here. Similarly, we have to go for all the blocks here. So this particular instant of blocks remain the same. Whereas for the first block, for the XOR operations, we input the initialization vector, and for the remaining blocks, the previous ciphertext for this one, the previous ciphertext for this one again, the previous ciphertext. The previous ciphertext will be the input to the XOR operations here. Okay, that is why the name comes here as a cipher block chaining mode here. The chaining comes from the previous block here. Okay, this is how we got the encryption method. From the plain text, we generate the ciphertext here. So if you want to write the formula for that, okay, what actually we are performing? We are performing first of all, we are performing the XOR operations here. If you take the second step, we are performing the XOR operations of P. For this P, again P, we are performing the XOR operations of P2, okay. With whom? With the previous ciphertext. With the previous ciphertext, okay. With the previous ciphertext, we are performing the XOR operations here. For that, I have written as XOR operations here. After XOR operations, I have to do the encryptions here. For XOR operations, I have to do the encryptions with whom? With the given key K. With the given key K, I have to perform the encryption algorithms here. Okay. I have to perform the encryption algorithm with the given key here. So if we write in general method, if we have taken the J step, okay, Z step, if we have performing for the Z step, then this will be Pj. This is Pj means this is Cj minus 1. When it is 2, it becomes 1 here. So when it becomes J, it becomes J minus 1. Then encryption with key, and then with a symbol of key E as encryptions here, then we got the ciphertext here. Okay, we got now, what is that? We got the ciphertext of the Z block here. So this is how you write the given formula for the given encryptions here. Okay, these encryptions may be, algorithms may be different. It may be the RSA algorithm, it may be the DSA algorithm, it may be the AS algorithm, but in general we have all simply taken as the E here, as an encryptions here. Okay, then obviously you have to know here, what is this IVE? IVE is the initialization vector. Okay, and then we initialize C0 as IVE here. So when you take for the first step, this is P1, then this is C1 minus 1. Okay, this is C, this will be C0. So what is it C0? C0 we have initialized to IV here. IV is nothing but the initialization vector here. Okay, initialization vector. So similarly, if you look at the decryption part, it follows the same procedures here. Okay, it follows the same procedure. We got the ciphertext blocks, we'll divide them into equal blocks. Then we have to decrypt it. It's just the reverse part. Here encryption, perform encryptions in the from C1 with encryptions here. Just do the reverse part here. Okay, C1 instead of encryption, we do the decryptions here with the given key, and then that result we do the XOR operations here. With this one, we do the XOR operations here, and then with the XOR operations, and then from the previous block we take the chaining mode, and then we perform the XOR operations here. And for the first step, we perform the XOR operations with C0. C0 is nothing but your IV here. Okay, initialization vector. So this is how we complete the decryption method of the cipher block chaining mode. So your modern cryptography technique will use any one of these given methods here. It can be the electronic code boot, it can be the chaining mode, or it can be the other mode that we will be doing in the next steps here. So if you want to write the formulas for the decryption part, you can follow this procedure. Okay, and this is how you get your plain text, the Z plain text in general. Okay, so what is one of the limitations here? What is one of the limitations here? Why we are going for this CBC mode? If you look at the electronic code book, because there is a redundancy of a particular ciphertext here. Okay, the ciphertext patterns can be same when the plain text blocks are similar here. Okay, so in these cases here, when P1 and P2 are of equal patterns, here we are performing the XOR operations with IB. Here is we are performing the XOR operations with a different patterns here. Okay, with a different patterns, and we are performing the encryption with K. We are performing encryptions with K here. Something is already changed here. Okay, here we perform the XOR operations with IB. Here we are not performing the XOR operations with IB, but it is changed with C1. So here, to get the redundancy, it is very limited here. Okay, to get the redundancy, it is very limited. But one of the disadvantages is that if I have an error here at C1, then it will propagate. Okay, it will propagate through all the steps here. If I have an error even in one bit due to some problem or due to some transmission problems, maybe the electric lightning, maybe the manipulations, when there is some, like when 1 becomes 0, 0 becomes 1, that particular bit error will be transferred or propagate to the other steps here. So this is one of the major disadvantage of the Cipher block chaining mode. But whereas it what does it do? It clears, or it has an advantage that it reduces the problem of redundancy that we face in the electronic code book. Even though it solves the problem of electronic code book, here we again face an error propagations here. So therefore we have to look for the next block mode where we can reduce redundancy and also reduce the error propagations here. Okay.